As opposed to an independent and repeated measure design on their own, a mixed design combines repeated measures and independent design. At least two independent variables are required for this type of design to be possible, but you can have more. Both repeated measures variables and independent measure variables must be present. You can use two repeated measures variables and one independent measure variable, or one repeated measure variable and two independent measure variables, and each variable can have different levels. By doing a mixed design, you are able to see between group variables alongside the repeated measure variable. If you are using the Easy ANOVA model, you must look at the graphs, descriptive statistics, and check the assumption of sphericity before reporting the results, but the multi-level approach does not require you to test for sphericity. We report effect sizes the same way as we did in the repeated measure scenario, which is by looking at the R value instead of the omega value. My research question looks at the extent to which a person's environment affects their learning scores. I have 10 young participants and 10 older participants that sat through a class in every possible environment and then took a test on what they had learned and received a score ranging from 1 to 30. Each class environment varied in its audio distraction level, so there was blaring music, two people having a conversation, and white noise, and in its visual distraction level, which had high visual distraction, average distraction, and no distraction. By combining these characteristics, I had 9 different combinations, and each combination was represented by one of my classroom situations. As such, my situations were made up of 9 different unrelated classrooms. There were classrooms with blaring music that differed in their visual distraction levels. One had high visual distraction, one had average visual distraction, and one had no visual distraction. There were classrooms with 2 people having a conversation in them that differed in their visual distraction levels. One had high visual distraction, one had average visual distraction, and one had no visual distraction. And the final 3 classrooms had white noise playing but differed in their visual distraction levels. So one had high visual distraction, once again one had average visual distraction, and one had no visual distraction. I had 2 sets of participants. One group was older and one group was younger. Over time, the participants learned the same subject in all 9 classrooms and took the learning score test after each situation. So my design has 2 repeated measure variables, the audio distraction with 3 levels because the classroom could have blaring music, 2 people holding a conversation, or white noise, and visual distraction with 3 levels because the classroom could have no distraction, average distraction, or high distraction. The people taking the test could be old or young, so I included the age of test takers as my between group variable. And this is what my data looks like. So that's the no distraction with blaring music and so on. Now I installed and libraried the necessary packages to run a mixed design. The package EZ is used to run ANOVA. The package ggplot2 is used to create graphs. The package NLME is used if you decide to use a multi-level model, which I did. The package PastX is used for descriptive statistics. The package Reshape2 is used for reshaping the data. And the package WRS is used for a robust test. Now I library them, which most should already be libraried from before, but and just did this because last time it didn't work. So now I'm attaching the data set, and it is now attached. The data set in Excel had a column identifying each participant and which row of data belonged to them, their age, so whether they were considered young or old, and their scores for each possible situation. There are 9 possible situations: high visual distraction with blaring music, high visual distraction with 2 people having a conversation, and high visual distraction with white noise, average visual distraction with blaring music, with 2 people having a conversation in the background and white noise playing, and then no visual distraction with blaring music, no visual distraction with 2 people having a conversation in the background, and no visual distraction with white noise playing. The data in Excel is in the wide format, so we must convert it into the long format for R to use. I use the melt function to do this. I specify, which is right here. I specify columns in the data that identify characteristics of the scores, such as from whom they originate, and the characteristics of that person using the id option, and columns that identify the scores themselves using the measured option. The measured variables correspond with the exact situation each person was put in. I have 2 variables that remain constant for each of the 9 scores: the participant from which the learning score comes from and their age classifications. I use the melt function to create a new data set in the long format. The columns of information are named participant, age, variable, and value by default, so I change them to the appropriate titles for my data set. I choose participant, age, situation, and learning score. The variable situation is a mixture of my two predictor variables, visual distraction level and audio distraction level. So I must separate the variable situation into two new variables that dissociate the visual distraction levels of the situation from the audio distraction levels of the situation. Did I run this one? No. So I run that, and then I run this one. I create a variable called visual, which specifies whether in the situation that the learning score results from had a high visual distraction level, average visual distraction level, or no. I use the GL, or no distraction, excuse me. I use the GL function to do this, right here. And the numbers in the function tell R that I want to create 3 sets of 60 scores. The labels option then specifies the names to attach these sets, which corresponds to the levels of visual distraction. This will create 60 rows with the label high distraction, 60 rows with the label average distraction, and then 60 rows with the label no distraction. I then create a variable called audio, which tells me what level of audio distraction was present in this situation, which is right here. To do this, I want 3 groups that each contain 20 scores, which will create the codes for the first level of visual distraction, then second, then third. We add a third value to the function that is the total number of cases, so 180, so that R knows for each level of the audio distraction to be applied to each level of the visual distraction. The GL function will repeat the pattern of codes until it reaches the total number of cases. I then display my data set to make sure it's correctly done, which is right here. And it was, as you can see, it's a lot of numbers. Next, I look at the descriptive statistics of each of the separate groups and for the combination of age, visual distraction level, and audio distraction level. I might have gone way overboard here, but I did the descriptive statistics for each separate group and then the combination of variables together. The combined levels of age, visual levels of distraction, and levels of audio distraction is probably the output we are most interested in. It was the last group of variables I entered into R. So let's get all the way down there. This is where you look at standard deviations and the means. And I think I forgot to run that one. Now, here's the one we're interested in, all the way at the bottom. The resulting output contains descriptive statistics, so mean, standard deviations, etc., for each of the 9 conditions split according to whether the participants were considered old or young. These descriptive statistics are interesting because they show us the pattern and means across all experimental conditions. So as you can see, it's the different 9 situations for old and young. I chose to do a multi-level model as opposed to the easy ANOVA approach because it offers a more flexible framework for analyzing my data. I will extend the repeated measures design from the previous chapter by simply adding the between group variable as the additional predictor. Before I can build the model, I must set the contrast. I choose to set a non-orthogonal contrast for audio distraction levels because the 2 people having a conversation in the room represent the norm. The key is that the baseline category is coded as 0 for all contrasts, so my baseline group of 2 people having a conversation is assigned a value of 0 in both contrasts. We then assign a value of 1 for blaring music and 1 for white noise playing. Contrast 1 compares the blaring music situation to the 2 people having a conversation situation. Contrast 2 compares the white noise situation to the 2 people holding a conversation situation. To set these contrasts, I first create the variables by representing each contrast, then bind them together and set them as a contrast for audio distraction levels. Here's the white noise versus conversation, and here's where I bind them together for audio. Next, I do this for visual distraction levels, which also has a category that represents the norm, and that is the average distraction category. Again, I will use this condition as the control against which to compare our 2 extremes of high visual distraction and no distraction at all. Therefore, I will again set the contrast code such that high distraction is compared to average distraction in contrast 1, and no distraction is compared to average distraction in contrast 2. And then I bind them together to be the visual one. I I also have a third variable called age. I don't have to set an explicit contrast for this variable because it only has two levels of young and old. Therefore, the default contrast will be fine. I checked to make sure that I'd set the contrast correctly by executing the name of the variable and looking at the contrast attribute, which I had, as you can see right here. And once again right there. In order to look at the overall main effects and interactions, I decided I needed to build up the model one predictor at a time from a baseline that includes no predictors other than the intercept, which is right here called baseline. So I specified the baseline model with the outcome predicted only from the intercept of learning score and used maximum likelihood to estimate the model. The random part of the model reflects the fact that there are two repeated measure predictors called visual and audio, which are nested within the variable participant. In other words, scores for levels of these variables can be found within each participant. In order to see the overall effect of each main effect and interaction, I added them to the model one at a time, starting with audio. So here's the baseline. This is where I add audio. Using the update command, I took the created baseline model and added audio as a predictor. I then did the same thing and added visual to the model, creating the step before including audio as a predictor. So this model includes both visual and audio as predictors. I then did the same exact thing and took the model just created and added age as a predictor. I then had to add in the interactions between pairs of variables, or the two-way interactions. There are three of these interactions made up from all the combinations of the three main effects, so audio and visual, audio and age, and visual and age. I added the interactions one at a time using the update command. So here's audio and age, visual and age, audio and visual. Each time I added a new interaction, I created a new model. Each time I create a new model, I use the model that contains all of the terms for the previous model and add an interaction. So the model audio age is created by taking the age-in model, which contains all of the main effects, and adding the visual and age interaction to it. The same configuration method was used to add the other interactions. I also had to create a model that included the interaction of all three variables, which is right here. I did this by using the same update command and used the model with all of the main effects and two-way interactions called audio-visual, and added the three-way interaction of audio to visual to age. Executing the command created a model called learning model, which contains all the effects and interactions, and is the final model. So right here. In order to compare the models, I listed them in the order in which I want them to be compared in the ANOVA. The output shows that the ANOVA first compared the effects of audio to the baseline. So here, this is where I run it. And this is, I'm going to talk in the order of these right here. The output shows that the ANOVA first compared the effects of audio to the baseline. By adding audio as a predictor, I increased the degrees of freedom by 2 because of the two contrasts that were used to code this variable. The level of audio distraction had a significant effect on learning scores with a p-value of 0.0002. Next, I look at the effect of adding the main effect of visual into the model. Again, the degrees of freedom are increased by 2, but this time the fit of the model is not improved because the visual distraction levels did not have a significant effect on learning scores, p equals 0.29. The next model tells us whether adding age improved the fit of the model. It did not improve the fit of the model with a p-value of 0.397, indicating that age did not have a significant overall effect on learning scores. This effect adds only 1 degree of freedom because it was coded with a single contrast. The next model shows that the audio and age interaction is also not significant with a p-value of 0.92. This interaction adds 2 degrees of freedom because audio is coded with 2 contrasts and age is coded with only 1. This non-significant interaction means that learning scores were not affected by the degree of audio distraction and not affected by the participant's age group. The next model shows that the visual and age interaction is also not significant with a p-value of 0.4, indicating that the effect of visual distraction did not differ according to the age group of the raters. The next model of audio and visual once again is not significant with a p-value of 0.13. This interaction adds 4 degrees of freedom because it is made up of 2 variables, each coded with 2 contrasts. This interaction term means that if we ignore the age of the participants, the profile learning scores across different levels of audio distraction levels is not different for high distraction, average distraction, and no distraction visual levels. The final model shows that the audio and visual and age interactions also not significant with a p-value of 0.229, meaning that the audio and visual interaction was not significantly different in young and old participants. This interaction adds 4 degrees of freedom because audio is coded with 2 contrasts, visual is coded with 2 contrasts, and age is coded with only 1 contrast. So we get a 2 by 2 by 1 equaling 4 degrees of freedom. By using the multi-level approach, I didn't have to worry about sphericity, and I was able to break down the effects of looking at the model parameters, which reflect the contrast that we use to code the predictor variables. I look at the model parameters by executing the summary function right now. These contrasts tell us nothing about the difference between the high visual distraction level and no visual distraction conditions, or the blaring music and white noise conditions, because they were never compared. We are able to tell from our data that no differences exist between young and old participants in terms of how they're affected by visual and audio distractions when trying to learn. Next, this took a while, I created my interaction graphs to help me interpret my findings. My first graph looks at the interaction between audio distraction level and visual distraction level. The graph shows the average learning scores of different levels of audio distraction levels when the situation also had high distraction level, which is shown with the red line, average distraction level, which is shown with the green line, and no distraction, which is shown with the blue line. First, I'm looking at the difference between the situation with blaring music and the situation with 2 people holding a conversation, right here. The learning scores in the no distraction and average distraction situations don't seem to change much, but for the high distraction level situation, the score increases. Now, if I look at the difference in the situation with a conversation occurring and the situation with white noise, learning scores increase for all visual distraction level situations. So learning scores are higher in the situation than in the blaring music situation, in this situation right here. Now I'll do my next one. Next, the graph looks at the interaction between age and audio distraction level situations. The graph shows the average learning scores of situations of different audio distraction levels, ignoring what visual distraction level is present. The graph shows young participants in green and old participants in red. The graph shows that the learning scores are extremely similar for old and young participants across the board. For the blaring music situation, older participants seem to handle the noise better by scoring higher than younger participants. For the 2 people having a conversation in the white noise situation, the scores seem to be almost the exact same for both old and young participants. The next graph looks at the interaction between age and visual distraction levels of the situation. The graph shows the average learning score of older participants ignoring the different levels of audio distraction in red, and it shows the average learning score of younger participants ignoring the different levels of audio distraction in green. For the high distraction level situation right here, it's in orange. Older participants had a higher learning score, but for the average distraction level, younger participants had a higher learning score. The last interaction graph The last interaction graph is the 3-way interaction between audio distraction level, visual distraction level, and age. It tells us whether the audio distraction level and visual distraction level interaction is the same for young and old participants. The results show the visual and audio interaction for old and young participants separately. The old graph shows that for the no distraction scenario, learning scores seem to stay the same from blaring music to the conversation occurring, but lower in the white noise scenario. For the average visual distraction for older participants, for younger participants, scores lower from the blaring music to the conversation occurring, but shoot up for the white noise situation. Lastly, for old participants in the high distraction scenario, scores continue to rise across from the blaring music to the conversation occurring to the white noise. So let me make that clear. All of those are for the old graph right here. I think I might have misspoke. Now we're moving on to this young graph right here. As far as the young participants in the high distraction visual level goes, scores slowly rose from the blaring music to the conversation occurring to the white noise scenario. The younger participants in the average visual distraction scenario showed scores to rise from the blaring music up somewhere in the conversation to the highest in white noise scenario. Lastly, young participants in the no visual distraction showed their scores to be in the middle for the blaring music situation, then dip down for the conversation situation, then rise to the highest in the white noise situation. Maybe they were getting distracted by listening to the conversation instead of the material they should have been learning. Next, I loaded and libraried the packages for using the function rContrast again because it is so weird when it comes to our R. So hopefully this works. Since my three-way interaction was not significant, I looked at the effect sizes for every level of my model. For the sake of time, I'm only going to talk about the effect sizes found in the three-way interaction towards the bottom once everything loads. Now we're going to library it. Now here's like all the contrasts I did, which I guess I'll run them for you, but we're just not going to discuss them. The bottom four are the three-way interaction contrast. There's a lot of them. Okay, so these are the effect sizes we're interested in. For blaring music versus two people having a conversation and high visual distraction versus average visual distraction and young versus old, the effect size is found to be 0.11. For white noise versus conversation, high visual distraction versus average, and young versus old, the effect size is found to be 0.03. For audio blaring versus the conversation occurring and no visual distraction versus average visual distraction, and young versus old, the effect size is found to be 0.11. For white noise and audio distraction versus the conversation occurring and no visual distraction versus average visual distraction, and young versus old, the effect size was found to be 0.17. None of the effects were significant, and therefore none of them yielded very big effect sizes.